Hi, today we will learn about ordinary linear differential equations. That is, the linear equation with constant coefficients of order n, a general form, is given by a naught nth derivative of y plus a1 n minus 1th derivative of y plus a2 n minus 2th derivative of y plus etc. plus an y equal to f of x, where all these coefficients a0, a1, a2, etc. an are constants. They are all constants. And f of x is a function of x. The operator d is equal to d by dx, dy is equal to dy by dx, d square y is equal to d square y by dx square, d cube y is equal to d cube y by dx cube. So with this notation, the given general form of linear differential equation can be written in the form of a naught. This is nth derivative of y. So instead of d by dx, we are using d. So a naught d power n, that is nth derivative, plus a1 n minus 1th derivative plus etc. plus an into y taken as a common term equal to f of x. This function alone, which is in the bracket, is denoted by f of d. Therefore, the function reduces to f of dy equal to f of x. Now, what are the laws of d? D of u plus v is equal to du plus dv. D power m, d power n u is equal to d power m plus n u. D of cu is equal to c du. D power m, d power n u is equal to d power n, d power m u. So having solved the linear differential equation using the properties of d and the laws of finding complementary function and particular integral, the solution should be written in the form of general solution equal to complementary function plus particular integral. So there are four rules to find complementary function and 4 rules to find particular integral, and some sub rules to find particular integral. Now let us learn the rules to find complementary function. So before we find the complementary function, the given differential equation should be written in a form such that in f of d we should put d equal to m and we should equate it to 0, f of m equal to 0. That equation is called auxiliary equation. Having found the auxiliary equation, we have to solve this auxiliary equation. It will be an algebraic equation. When we solve it, the possibilities are that we will get real and distinct roots, real and repeated roots, imaginary and distinct roots, and imaginary and repeated roots. So we know that if it's a quadratic equation, that is when the degree of the equation is 2, then we will get 2 roots. When the degree is 3, cubic equation, we will get 3 roots. So based on that, we will judge whether the roots are real or distinct. Now case 1, when the roots of f of m equal to 0 are real and distinct, say m1 equal m1, m2, m3, etc. In that case, the complementary function should be written in the form of c1 e power m1x plus c2 e power m2x plus c3 e power m3x plus etc. So we will extend it up to the number of roots we've got. Case 2, the roots of f of m equal to 0 are real and repeated twice, say m1, m2. So the roots will be same, it will be repeated. That is, we will equate it to m1 equal to m2 equal to m. In that case, when it is repeated twice, we will write CF as c1 plus c2x e power mx. When the roots are repeated thrice, say m1, m2, m3, that is m1 equal to m2 equal to m3 equal to m. In that case, we will write CF as c1 plus c2x plus c3x square e power mx. Case 3, roots of f of m equal to 0 are imaginary and distinct. Then the roots will be in the form of alpha plus or minus I beta. Then the CF will be written as alpha, that is, we know that imaginary root means it is a complex number. It will be written in the form of alpha plus or minus I beta. The coefficient of I is the beta value. In that case, complementary function should be written as e power alpha x into c1 cos beta x plus c2 sin beta x. In case these roots are imaginary and repeated twice, then it falls in case 4, and the complementary function will be e power alpha x into c1 plus c2 x, because it is repeated twice, the same way like real and repeated twice. So c1 plus c2x cos beta x plus c3 plus c4x sin beta x. So c1, c2, c3, c4 are all constants. We can also use a, b, c, d. It is just used to denote the constants. Now going ahead, let us see how to find the particular integral. Again, to find particular integral, there are 4 cases. So before we discuss the cases, we need to understand that the particular integral should be written in the form of 1 by f of d f of x. Now case 1, f of x is equal to e power mx. So if the right hand side is in the form of e power mx, all we need to do is write it in the form of 1 by f of d f of x, put d equal to m which is the coefficient of x, and solve. In case after we substitute f of m, the denominator becomes 0, then we have to use this formula e power mx phi of d into x power r by r factorial, where m is the root of f of d equal to 0 repeated r times. That is, f of phi of d is the non-zero value. We should see how many times a 0 factor repeats. Therefore, whenever we have e power mx on the right side, we should always write the denominator in the form of factors. Now going to case 2, f of x is equal to cos mx or sin mx. Then 1 by f of d square. So in this case, only for d square we have to substitute, not for d. So for 1 by f of d square cos mx, we should substitute d square equal to minus m square. Then the function reduces to 1 by f of minus m square cos mx, and 1 by f of d square sin mx equal to 1 by f of minus m square sin mx. So we need to note that after substitution, we have to sometimes rationalize to make d as d square and again substitute for d square term. So whenever we are using case 2, we can substitute only for d square. So to make d as d square, we have to rationalize and make d as d square. So we will discuss about it in the problems. And sometimes it is possible that when we put d square equal to minus m square, the denominator becomes 0. In that case, we can use this ready formula 1 by d square plus a square sin ax. So when we put d square as minus a square, it becomes 0. Then the solution should be written as minus x by 2a cos ax. 1 by d square plus a square cos ax is equal to x by 2a sin ax. So that is case 2. Now case 3, right hand side is a polynomial. Whenever right hand side is a polynomial, so we know that to find pi, we should write it in the form of 1 by f of d x power m. So 1 by f of d should be written as f of d inverse. So when we take inverse, we should use any of these 4 formulae. So 1 plus d inverse is equal to 1 minus d plus d square minus d cube plus etc. 1 minus d inverse is equal to 1 plus d plus d square plus d cube plus etc. 1 plus d power minus 2 is equal to 1 minus 2d plus 3d square minus 4d cube plus etc. 1 minus d power minus 2 is equal to 1 plus 2d plus 3d square plus 4d cube plus etc. So we know that d is first derivative, d square is second derivative, d cube is third derivative. So we will write it here in the expansion and multiply it with, apply it to the polynomial or the algebraic function given. That is case 3. Coming to case 4, f of x equal to e power mx v, where v is any function of x. In this case, we will write the given function as 1 by f of d e power mx v. So to apply To use case 4, d becomes d plus m, which is the coefficient of x in e power mx. So it will be e power mx into 1 by f of d plus m v. At this stage, sometimes it is possible that v can be a trigonometric function or a polynomial. If it is a trigonometric function, we should use case 2. If it is a polynomial, we will use case 3 and write the solution. So having found particular integral and CF, solution should be written as general solution equal to complementary function plus particular integral. And that is the final answer. Thank you.